Good morning, everybody. Welcome to another Power Place Summit Wednesday webinar. I think this is our fourth one. Glad you can join us. Today we're going to be covering a really important topic that we've been heavily involved with for a few years now, really. The title of this webinar is We Need the Forest to Fight Climate Change. You can see our panelists' names below. I'm going to let Scott introduce them as they get ready to go. But today on deck we have Scott Millar. He's the Director of Community Assistance and Conservation with us here at Grow Smart, Rhode Island. We have Frank Lowenstein, Deputy Director of the New England Forestry Foundation, and we have David O'Day, Principal of O'Day Engineers. So thank you guys so much for being with us this morning. My name is CJ Oberthauser. I'm the Director of Training and Placemaking with Grow Smart. We obviously wish we could be holding these in person during our Power Place Summit, but we're really happy that we're able to have these every single Wednesday this summer and even kind of early fall almost, leading up to a big plenary half-day session replacing our in-person summit, which will take place on September 25th. Again, these panels are happening every single Wednesday. You can find a full lineup on our website. If you have a ticket for the summit, it's all included. If you do not, you can still access each one for $10 a piece. So you can kind of pick and choose from the menu, again, on our website. On the half-day plenary on September 25th, we're going to be featuring Scott Spencer of Smart Growth America and the Annie E. Casey Foundation, along with award-winning columnist E.J. Dion of the Washington Post and the Brookings Institution. We're going to have a couple other speakers that we're working on right now and some panels that are very exciting, so stay tuned for more info. We also want to make sure that we thank our sponsors, so I'm going to put this screen up so they get some recognition. Obviously, we couldn't do this without them. Little housekeeping stuff as well. The full speaker bios will be available on our website, so head there to learn more about these gentlemen and all of our other speakers. And all of our webinars have been approved for one AICP credit. So if you're seeking those, you can hop on the AICP website and input all the info that they need, and you can get your credits from this and all of our Wednesday webinars. Please feel free at any time to send in a question in the Q&A function here in Zoom. We will get to them at the end, but as you send them in, we'll save them. They're not going to go anywhere. So as soon as you think of a question, feel free to enter it there. And lastly, this session is being recorded, so all of you and everyone with a summit ticket will be able to watch this. I think within a few days, usually we're sending these out. So if you're joining us a little late, don't worry, you're gonna be able to catch up. And with that, I will stop talking and I will hand it off to Scott Millar.
Thank you, CJ. Good morning, everyone. I'm going to be the moderator for today's session. We need the forest to fight climate change, and that title clearly states one critical value of Rhode Island's forests. Historically, Rhode Islanders have taken our forests for granted, despite their value for clean air, safe drinking water, a multiple list of outdoor recreational opportunities, and very valuable habitat. Moreover, Rhode Island's wood products contribute over $700 million annually to Rhode Island's economy. To be successful in combating climate change, we need to achieve two very broad objectives simultaneously. First, we must stop carbon emissions as soon as possible. That's absolutely critical. I think everyone understands that. But second, we must also remove carbon that's already in the atmosphere and store it long term. Renewable energy can only prevent future carbon emissions. The forest can achieve both objectives. But most policymakers, unfortunately, are not aware of these forest values and aren't taking any meaningful actions to conserve our forests. So our first speaker today is Frank Lowenstein. Frank is the Deputy Director of the New England Forestry Foundation. Frank leads the organization's Center for Forestry and Conservation Innovation. The center develops creative approaches to accelerate conservation and advance exemplary forest management in New England's woods. Frank also worked for more than 20 years for the Nature Conservancy. At the Nature Conservancy, he led the organization's Global Climate Adaptation Program. He is a former senior fellow in the U.S. Department of State's Energy and Climate Partnership. He is the author of 3 books and an adjunct faculty in environmental studies at both Brandeis and Harvard universities. Frank will present using forests and wood to combat climate change. Frank, it's all yours. Thank you for joining us.
Okay, there we go. Thank you, Scott, and thank you everyone out there in Zoom land. I'm going to go ahead and share my screen so that you guys can see my presentation. Okay, so should be good to go there. So I want to just briefly acknowledge my co-author here, Jennifer Shacken, who's our climate forest specialist at New England Forestry Foundation. She does a lot of our work on the linkages between climate, forests, and wood buildings. We really see that as a systems approach and as a key piece of helping to achieve New England Forestry Foundation's mission, which is really to help protect the way of life of everyone here in New England, protect wildlife, ecosystem services, and also address global climate change. This mission was updated by our board of directors about 1.5 years ago. And at that time, that was the first time we added climate change to the core mission of the organization. And the reason for that is that we see climate change as a critical challenge that threatens everything that all of us value here and love here in New England. This graph is from the IPCC's October 2018 report on the difference between 1.5 and 2 degrees Celsius. And this is the most complex graph I'm going to show today. And I think I only have 3. This one is showing past emissions and temperatures, and it's showing what might happen between now and 2030 to 2052. And it's basically forecasting that we're going to cross the threshold that scientists have identified as the threshold to dangerous climate change of 1.5 degrees Celsius average rise as soon as 2030. That is around the corner. You know, I'm already saving for college for my formerly middle school, now going into high school kid. And he's going to be still probably in graduate school in 2030. You know, so this is in the planning horizon that many of us use in our personal lives, and we need to make unprecedented reductions in emissions in order to avoid not only exceeding 1.5 degrees Celsius, but then even exceeding 2 degrees Celsius. And the damages rise exponentially with every fraction of a degree that we go up. You may have seen when this report came out that the difference between 1.5 and 2 degrees Celsius is something on the order of I believe it's $41 trillion by the end of the century in differences in damages. What wasn't highlighted in a lot of the press reports is that the difference between 2 degrees Celsius and 3.6 degrees Celsius, which may be where we're headed if we don't reduce emissions, is over $400 trillion in damages. I always want to say billion. Trillion just sounds so big, but it's actually equivalent to the value of all infrastructure on the planet today. Every building, every airport, every highway. Just imagine erasing those and having to start over from zero. Of course, we will be building a lot of additional infrastructure between now and 2100, but we're going to waste a lot of effort unless we restrain climate change. The reason for that was well highlighted in a report from McKinsey Global Institute that came out at the beginning of this year. And it's long been known that minor differences, relatively minor differences in average temperatures produce big changes at the extreme. As you shift the average a little bit, events that were previously rare become more common, and events that were previously unheard of start to occur. And we are actually, scientists have been forecasting this for years. Now we're actually starting to see it happen. So this report, for example, notes that unusually hot summers, which covered 0.2% of the planet per year prior to 1980, in 2015 were occurring across 15% of the planet. And extremely hot summers that didn't occur at all prior to 1980 are now covering half of 1% of the planet. The more we increase the average temperature, the more these extremes come, and those are what are going to damage us here in New England. Now in Rhode Island, I think we should be very concerned about, of course, coastal flooding and strong hurricanes, but in terms of the forest, we're going to see more heat waves, we're going to see more droughts, we're going to see more floods, and we're going to see more extreme winds and storms. Climate variability is going to increase. So what can we do, and what can the forests do for us to help prevent this? Well, forests, of course, store carbon in the boles and trunks and leaves of trees, as well as in the soils of the forest. They are the best terrestrial mechanism that we have for removing carbon from the atmosphere. And in the forests of the world today, there's actually stored more than twice the total carbon dioxide that's in the atmosphere. So if we lost all of the world's forests today, the atmospheric carbon dioxide levels would more than triple. So we don't want to do that. That would be game over in terms of climate change. So how do we best use the forest? Well, we've been using forests for a long time. We use them for a source of renewable, sustainable wood products. Those wood products store a portion of the carbon that is in the living trees. So is there a way that we can both optimize the amount of carbon that we store in forests and use wood products to store some of that carbon permanently in our products and particularly in our cities? Can we think of our forests and our cities as an integrated link, an integrated system that pumps carbon out of the atmosphere and locks it away? And we at New England Forestry Foundation think we can. That systems approach requires three things. It requires ending forest conversion. It requires improving forestry, improving the practice of how we manage our forests so they store and remove carbon dioxide better and actually also grow more, and using that extra growth for long-lived wood products that we can lock away. And when you put all that together, we get what we call a new climate wedge. For those of you who may not remember it, Pakala and Sokolov from Princeton University came out in 2004 with the idea of climate wedges. These were going to be a series of actions that we could take that, when combined, were going to reduce carbon dioxide levels to a point where we could get to where we could implement new technologies that would eventually reduce or eliminate carbon dioxide emissions. We think that one of those wedges can be the systems approach to forests. So this is a new graph. I've never used this one before. I think it's my last chart of the presentation. So the wedge that we're talking about combines a few things. It combines improving the management of the forest and storing more carbon in living forests. That's that top blue wedge. The other three, storing wood in buildings, avoiding forest conversion, and avoiding emissions associated with creating concrete and steel, those three are associated with the wood buildings. And combined, the best estimate that we're familiar with on how much of a difference this could make is from Chad Oliver at Yale, Oliver et al. 2014, if any of you want to look it up on Google Scholar. That study said that to eliminate the total emissions currently associated with the construction sector, around 10% of global emissions, we would need to increase harvest of forests from the current 20% of annual growth to 34 to 58%. And by doing that and directing that harvest into efficient wood products, we could essentially eliminate the emissions from the construction sector. That's big. If you can do something renewable and sustainable and eliminate all the emissions from construction, that is huge. And if we improved forestry, that percentage of extra growth would be less because we could grow more each year. So let's dive in just a little bit into this. So thinking about the first piece of forest conversion, forest conversion is a big problem because you're not only releasing the carbon that is on that land today, but you're eliminating the future potential growth. Currently, across New England and even here in Rhode Island, we're seeing a lot of loss of forest, not just for sort of homes, suburban development on the edges of urban areas, which has been our traditional way that we've lost forest cover in recent years, but also now loss of forest for solar farms, like the new one that's been approved in North Smithfield. That is a permanent loss of forest storage capacity, is a permanent loss of one of the things that we can flexibly manage to respond to climate change. So how do we end forest conversion? Well, land conservation can be a key part of it. New England Forestry Foundation has conserved about 1 out of every 8 acres of land conserved in New England since the start of the land conservation movement in the late 1800s. We have about 1.1 million acres of conserved land. That's about half again as big as Rhode Island. So that's a good strategy, and that can work, targeted land conservation, but it's not enough. We also need better land use planning and probably zoning and incentives for landowners. The second piece here is managing forests better. And I want to highlight that this is really key. We can both maintain stocking in the forest and increase growth and harvest at the same time. Harvard Forest, in their changes to the land study that was published in late 2013, early 2014, highlighted that their forest as infrastructure scenario, the far right one on your screen, could hold 96% as much carbon in the living forest while doubling production of wood in Massachusetts. That's in heavily forested Massachusetts. In places like northern Maine and northern New Hampshire, where the forest has been pretty heavily harvested for a long time, and that harvest has reached a point where it's actually suppressing the growth of the forest. You're not optimizing the growth because there's not enough stocking on a given acre of land. There's not enough trees to capture all the sunlight. No, it isn't quite enough trees. There's not enough leaf area. That in those landscapes, we could do far better than we can do in a heavily stocked landscape like Massachusetts or like Rhode Island's forests. New England Forestry Foundation is putting forward principles of exemplary forestry. This is our approach to doing that enhances wildlife habitat, improves the quality and quantity of wood production, and gives us a chance to really use our forests as best we can for climate mitigation and adaptation. We've put those forward for the Acadian forests of northern New England, the northern hardwoods and spruce fir forests. We're currently working on it for the central hardwoods and oak pine systems of southern New England. Okay, so if we did this, how much could it help? Across northern New England, if we applied those Acadian forest standards, we could store another 1.9 gigatons of carbon dioxide in new living wood. And we believe we could do that while maintaining harvest. If achieved over 20 years, that would be equivalent to removing every vehicle in New England off the roads in the same time period. And by vehicle, I don't just mean cars. I mean cars, trucks, tractors, ATVs, SUVs, whatever you want to talk about. So that could be big. The final piece here is long-lived wood products. And I know David's going to cover this in much more detail. And the first piece here is we think that there's a tremendous opportunity to build more wood buildings. And we need to do that. We need to do that for housing equity. The Metro Mayors Coalition in Boston has identified that in Metro Boston, we need another 185,000 new units of housing by 2030. Same time frame as we're trying to prevent going over 1.5 degrees C. How do we do that? How do we build another 185,000 new housing units without cooking the climate due to the emissions from concrete and steel? Well, I've pretty much already told you that the way we can do it is through wood buildings like this one that David's going to be featuring much more at RISD. These wood buildings help the climate 3 important ways. It takes far fewer emissions to build a building using mostly these engineered wood panels, cross-laminated timber, glue lam, nail laminated timber, these new products. And cross-laminated timber has only been used in construction since the mid-2000s in Europe. It's now approved in the code for buildings up to 18 stories high. That's the 2021 version of the International Building Code. That will be adopted in Massachusetts on January 1 of next year. So at that point, you can go up to 18 stories without having to do special studies and permitting. So when you're building with wood, you're not making steel and concrete, you're not heating those materials up to 2,500 degrees Celsius or higher, and therefore you're saving emissions. The second piece is you're sequestering wood in the building. This is the 18-story Brock Commons dormitory at the University of British Columbia. Concrete cores for the elevators that help give the building vertical stability, together with CLT walls and floors. And you're storing thousands of tons of carbon in that building. You're turning your buildings from a source of emissions between those two efforts, from a source of emissions into a sink, into a place where you can store carbon from the atmosphere permanently, at least for the life of the building. And if we think about how do we recycle the buildings, how do we recycle the wood, turn it into 3D printing plastics, turn it into biochar that we use to increase agricultural productivity, we can really extend the life of that sequestered carbon. Finally, these new wood buildings are economical in the 6 to 12 story range that people don't tend currently to build housing in. And by not using that 6 to 12 story range, which is uneconomical to build with steel and concrete and too high to go stick built with, we're losing density around transit hubs. And that, you know, if we're not building, having people live near transit hubs, where are they going? They're spreading out across the landscape. This is the Treat Tower in Bergen, Norway. I've actually seen this building. It's beautiful, and it is completely different from current housing in Norway and incredibly popular. So this is the approach, but it's really important to highlight that it is super important that we source these materials from sustainably managed forests, and they have to be sustainable for climate change. Currently, third-party certification of forestry has not caught up with this idea. This picture is one that I took. That is an FSC certified piece of property, which is the gold standard of third-party certification today. And there's clearly not a lot of carbon standing on that property, not a lot still stored on that property. The certification systems are wrestling with how to catch up with this. So eventually that will be fixed. But right now, it's super important that architects and engineers and planners think about how do they build sourcing requirements into their specifications that drive not only for that third-party certification, but also for a climate-friendly approach to forestry. We really think that there's a role for both living forests and forest products in solving the climate crisis. We see this opportunity to end forest conversion, which requires policy changes, combined with better forestry, combined with long-lived wood products and these new approaches to construction to achieve this new climate wedge. And if we can do that, what do we get? Well, we get forest products at the center of climate-driven development. We get more jobs in depressed rural communities. We get more housing with more affordable pricing that can help address some of the income inequalities and racial inequity in society. In addition, I think that you're tying the city to the rural areas, which can help bridge some of the political divisions in our society. We can improve mobility and reduce future sprawl through more concentrated development around transit hubs and maintain the benefits that we really need from our forests: clean air, wildlife habitat, clean water. And how do we do it? Well, continue to continue to support land conservation. The passage this week of the Land and Water Conservation Fund through the Senate and the House now was super. Stop and limit conversion of forest land to other uses. With respect to exemplary forestry, we've got to provide incentives to private landowners for them to adopt exemplary forestry, and sourcing requirements can help drive towards that. And with long-lived wood products, we need to increase both demand for them and the local supply. Right now, we don't have a cross-laminated timber plant in New England. A lot of companies are thinking about building one. They're waiting for a signal that the demand is there. Put it together, and we have a bright future with helping to solve the climate crisis. Thank you. Here's my email and Jen Chackin's email. Please feel free to contact us with any questions that you don't have an opportunity to get addressed here.
Frank, that was excellent. I think we've got about 5 minutes or so for questions before we turn it over to David. CJ, do you have any questions that came in that you want to share?
Yeah, we do have one question. Here's the question. What is the impact of using wood as a fuel? Is that not recommended?
Oh boy, so that is an incredibly complex issue. My general take on it is that when you are harvesting wood with the intent of using the harvest for fuel, you're probably not doing the best thing by the climate. When you're using trees that you need to thin anyway and that naturally would have died anyway, or when you're using tops and limbs from other trees that you've harvested, or when you're using wastes from the milling of wood, then it potentially can be a contributor to a systems approach. But in the long run, I hope that we will get to uses for small diameter trees that don't require those to quickly be returned to the atmosphere. Things like the new wood fiber insulation plant that's going up in Maine, where we'll be able to make wood fiber panels that will replace the extruded foam panels that you see on a lot of buildings. Or also at the University of Maine, they have the world's largest 3D printer that is printing plastics made from small diameter wood. Those are better solutions because you're locking up the carbon for longer. So biomass energy may have a role, but it's definitely not the focus.
All right, so we have a bunch of questions. Scott, how long did you want to do questions for this little chunk of time?
Scott,
you're still muted, Scott. Scott, you're still muted.
Sorry. We've got about 2 more minutes, and then we'll go to David, but we will reserve some time at the end we can come back to Frank to ask additional questions.
Okay, great. I'll do one more question. I think this might kind of kill two birds with one stone. You have two questions that are kind of similar. Are there good options for those of us that control only a few acres of second growth woods?
So yes, absolutely. You can take actions to store more carbon in your woods and to increase the resiliency of your woods in the face of these extreme climate events that are coming. You can find information about that on New England Forestry Foundation's website at newenglandforestry.org, or contact me and I'll put you in touch with some of those resources. The NIAX program at the U.S. Forest Service is also working to provide that kind of information to small landowners. In general, it's not going to be efficient under today's economic and harvesting systems to harvest wood from small parcels. It's probably not your best option.
Let's take one more, CJ.
All right. So this one might work. Please speak more about incentives for private landowners.
Oh, sure. So essentially, when we talk about exemplary forestry, we're talking about implementing better silviculture. We're probably talking about lengthening rotations so that the time between harvests is longer. In the short term, in the long term, that will actually provide benefits to the landowner. They'll see more income because larger trees, older trees, will actually sequester more carbon, grow more wood per acre per year. And so that's good for the landowner. But there's a time gap. It takes 20, 30 years to grow those bigger trees. A lot of landowners can't wait 20, 30 years for their income stream that they've been expecting. So if you're dealing with landowners who are owning forest land for financial reasons, as opposed to heritage reasons or because they love the woods, you really need to think about how do we help them bridge that time gap? What sort of financial incentives can we provide them that would help them get to those larger trees and longer rotations. And that could be tax incentives, that could be payments for carbon stored, that could be things like NRCS, Natural Resources Conservation Service payments to landowners to help them improve practices. And some of the NRCS practices are moving towards more carbon storage and longer rotations. So those are the kinds of incentives that are needed. There could also be market incentives, again, that would have to be driven by sourcing requirements coming out of the architecture and engineering and development community.
Again, that was excellent. Thank you, Frank. I think we're going to have some more time at the end so we can have some additional questions. But now
Thanks for the great questions, everyone.
They were. Now that we have a very good understanding why it's critical to reduce our new construction with concrete and steel and use more wood, we're going to turn it over to David O'Day. David has been doing some innovative use with cross-laminated timbers. David is a principal at O'Day Engineers. It's a leading structural engineering firm headquartered right here in North Providence, Rhode Island. David grew up in Rhode Island, attended Brown University. Following his time at Brown, David went to graduate school at the University of California at Berkeley, started his career as a structural engineer in San Francisco. Later, he made his way back to New England to join O'Day Engineers, a company founded by his father. I'm sure his father's very proud. Over the last 20 years, the two have worked together to grow the company to over 40 employees and national prominence for its innovative technology and designs. Recently, O'Day has been a leader in engineering of large-scale mass timber structures, including the RISD North Hall building that David is now going to discuss. David?
Thank you, Scott. Thanks, Frank, for that great presentation. It's a pleasure to be here with you today. I'm coming to you today from my office in North Providence, which is our home for O'Day Engineers and has been since our inception back in the early 1980s. This is a picture of the room that I'm in from another angle. We call it our building information model immersion room. It has kind of an IMAX size screen which we use to collaborate with our clients and develop designs for building structures using digital design tools that we've developed both here in-house and that we use with our partners, who are typically architects, developers, builders, government agencies, and other types of clients. Our firm has its base here, but we really work all over the country, which is great. We also have a small office in Boston. And our goal is to bring the most innovative design tools and technologies to structural engineering for our clients to help them with their projects, some of which I'll share with you today. I'll spend my time today on 4 key topics. Frank has given you a great introduction to, I think, some of the impetus in the design world to using timber products more frequently in construction. I will speak to you a little more specifically about this idea of mass timber, what it is, where it came from, and why people are pretty excited about using it in structures today. I will briefly touch on some of the sustainability benefits of mass timber. I think Frank has really covered that adequately, but I'll just say a few words about embodied carbon and how that's being used by the design profession. I'll talk about the building code. A lot of people ask me questions about, well, what can I actually build with mass timber products? I'll talk a little bit about Rhode Island's building code, which is similar to other states in the US and what it allows now and what is coming down the pike with some new versions of the code that have been approved. And last, I'll finish by talking about some examples, including, I think, a really innovative project that we did here with our partners at the Rhode Island School of Design to build a new dormitory, which now graces College Hill and is one of the first large-scale structures in New England built using cross-laminated timber. But let's start by first talking a little bit about heavy timber and what it is. What do we mean when we say heavy timber and mass timber? Well, heavy timber and using timber for construction is not a new concept. We know that in Rhode Island because we were the home and the genesis of the Industrial Revolution in the United States. And that's really where heavy timber started to become a really important part of the construction of our built environment. One of the key reasons that heavy timber became very popular as a building material was because of its characteristics related to fire. Buildings such as some of the ones you see here on the screen are historic structures in New England that were built using these methods. And they've been around for many hundreds of years, centuries in fact, in some cases. People often ask me about the durability of wood. One of my favorite projects that I've worked on in my career here in New England is the oldest timber frame church in the United States, the Old Ship Meeting House in Hingham, Massachusetts, which has been around since 1681. So wood structures can last a really long time if they're well maintained, and in particular if they don't burn down, which is a key issue with wood because it's a combustible material. Heavy timber has this characteristic of slow burning. There's a very large surface to volume ratio of large solid sawn lumber products, which if you've ever tried to create a fire in your fireplace with real wood, not those fake logs that they sell at the supermarket, you know it's pretty hard to start a fire with a log and keep it going. I'm terrible at it. That's because wood, such as large wood members such as these, form a charring layer on their exterior that's almost like insulation during a fire. It keeps the fire from further burning the structural fibers on the inside of the wood. So we call that slow burn. Unfortunately, the disadvantage of this construction approach is that it requires very large timbers to build with if you use the historical methods. You need a lot of big trees to make buildings like Old Ship or some of these old mill buildings, which we're all so familiar with here in New England. That is not a sustainable practice to harvest such large timbers. It takes a very long time for them to grow. That led to that kind of lack of that resource, led to really the preponderance of using, instead of heavy timber, mineral-based construction systems: steel, concrete, cement, masonry, other materials made from from minerals, as the primary construction system for much of the 20th century. That is changing because of advances in technology in timber, some of which Frank alluded to, that now allow us to use smaller trees, more sustainably harvested wood materials, to create better, more structurally optimized timber products that can be used in construction to solve challenges with structural engineering, such as creating structures with long spans, like you can do with steel, that are lightweight and can be very tall, and that preserve those properties of fire resistance that are so desirable in heavy timber buildings of ages old. Generally, such products are now called mass timber. That is the generic name for products that are what are known as engineered wood products that are laminated together. They're glued together using structural adhesives or finger jointing or other types of joinery to create structural members that are optimized for structural performance. You may be familiar with some of these from the past. It's not a new technology. The examples on the left show you two types of mass timber that are very popular and have been since the middle of the 20th century. Glue laminated lumber. There's a lot of glue laminated timber buildings that are still built today. It's a very popular material. That's made from laminating together boards of lumber, gluing them together like this beam you see. Something called an LVL or structural composite lumber more generally. That's really a lot more like plywood that uses veneers of lumber that are glued together to use as beams or headers or plywood, floors like plywood. But I'd like to focus today on a newer product that's becoming more popular that Frank alluded to as well, called cross-laminated timber, or panelized wood products that are made from smaller structural sections that are made from green lumber, from smaller trees, that are placed together in panels, in large-scale panels, and using joinery techniques can be produced in very long lengths so that they can cover large surfaces and have structural properties that are of use to engineers and architects in building buildings. The type in particular that's become very popular it became popularized in Europe and Austria actually for use in residential construction, is called cross-laminated timber. There are a number of manufacturers of this product in the United States and Canada. Cross-laminated timber in general is a mass timber panel product that consists of what are called layers, or sometimes called lamella, of structural boards, structural members that are laid up in a crosswise pattern. This is similar to the way plywood is constructed, for those of you who know wood construction, in that each layer is orthogonally oriented so that the structural fibers in wood, which are what do the work for the structure, which can resist the loads and the stresses in the wood, are oriented in the directions that we need them to be in order to best resist bending forces and other forces that we introduce to them. These panels are very exciting because they can be manufactured in very long lengths. Presses today by manufacturers available to us in New England can make up to 65-foot long panels. They can be 6, even up to 8 or 9 feet wide. So they can be shipped very efficiently to a site, prefabricated, and used as walls, floors, and roofs. They're panelized products that are often used this way. For those of you who are designers, CLT, or cross-laminated timber, is a product that's accepted in the building code today, as long as it's manufactured there's a joint North American standard called PRG 320 that is accepted in the code. And again, many manufacturers that supply products using this. Why is everyone so excited about mass timber products like cross-laminated timber? Well, I think it's Frank hit the nail on the head. It's the idea of reducing the carbon impact of building construction. Now, it's been known for a long time that in research of carbon emissions, that buildings and architecture in the built environment account for a very large portion of the greenhouse gas emissions that are the known driver of climate change and the ill effects that we've seen. Building energy usage as a whole represents about 40% of those emissions. So it's a huge amount of greenhouse gas emissions. Over the last 20 years, architects and engineers have really recognized this and focused on creating more sustainable buildings. But a lot of what we've done has not focused on the building structure itself. We focused on the operational energy of the building because, for good reason, that like the mechanical systems and the use of fuel to operate a building really represents a good chunk of the greenhouse gas emissions. But at least 10 or 20% of the emissions are really embodied in the structure and materials in the building themselves. One thing I wanted to mention to you today is that, I think Frank's covered the idea of carbon emissions well, is that engineers and architects are starting to use a measure of that carbon impact of buildings called embodied carbon when we design our structures. Embodied carbon refers to the total CO2 emissions or equivalent CO2 emissions associated with material production, fabrication, transportation, and erection of the building itself. So it's separated from the operational or mechanical systems and plumbing and those elements of the building. The largest component of this embodied carbon is in the building superstructure and the foundations. So it means that the structural engineer, which is what I do for a living, I design the parts of the building that make it stand up. Sometimes you see those parts, sometimes you don't. We like it when you see them because that's the mark of a good, elegant structure. But that represents a good chunk of that embodied carbon. We can measure that for different materials with some degree of accuracy. There's been a lot of research done recently. There's a great project that's underway by the Pankow Foundation called the EC3 project that's focused on creating a database of embodied carbon. I'm showing you here some information from the Carbon Leadership Forum that I would suggest you follow up on if you're interested in this topic. And also a paper by that was co-authored by a good friend and colleague, Alan Organsky, who is an architect on the faculty at Yale University and also a principal at Gray Organsky Architects. They're a frequent collaborator of our firm in mass timber structures, to show that the embodied carbon of timber structures, mass timber structures, can be greatly reduced when compared to other mineral-based materials, not just because the amount of embodied carbon per ton of wood is lower, but because wood structures tend to be lighter. But most importantly, as Frank described, such wood structures can be shown to sequester carbon. So these young trees that are harvested to create mass timber products like cross-laminated timber they've cleansed the environment of carbon dioxide through the miracle of photosynthesis, which creates sugars from water and carbon dioxide in the presence of sunlight. We take them, if we permanently put them in a building, and as long as they're kept in that building in perpetuity or recycled somehow, not burned and reoxidized back into the environment, and a new tree is grown in that tree's place, we create this virtuous cycle that Alan and his colleagues have done a lot of research on to show can have a real positive impact on bending the curve of climate change. So that's a summary of what mass timber is and kind of some of its ecological and sustainability benefits that I think architects and designers and builders are getting really excited about today. Now, how can you actually use these materials? There are newer materials. Some of them have been around for a long time, like glue laminated timber and just solid sawn heavy timber beams. But what about cross-laminated timber and other similar products? Well, the building code today, through most of the United States, follows a model code called the International Building Code. It's only used in the United States. I don't know why we call it the International Building Code, but that's our conceit, I guess. But this code is exactly what we use in Rhode Island. We use the 2015 edition of it. There's a newer edition, which we haven't adopted yet. And these codes limit, primarily because of fire resistance, they limit the use of different types of materials based on the type of construction, what's known as the type of construction. And the type of construction limits the height of the building, the area of the building, and the number of stories of the building that you can build. You may be familiar with light frame wood construction, which is very popular right now in Rhode Island and throughout New England. Light frame structures are typically either type 3 buildings or type 5 buildings. Both of them allow the use of combustible materials, which wood is always a combustible material. But you can see they have height limits depending on the occupancy that you have. So right now, if you want to build a light frame wood structure, you can build it up to 5 stories and 85 feet in height if it's a type 3A building. There's a lot of buildings like that right now. If you're familiar with downtown Providence, we just did a type 3A building on Fountain Street, brand new. Has a fire protected, non-combustible exterior, but it's light frame wood construction on the interior. It uses something called a podium to increase its number of floors. It's actually 6 floors. It's not 5 floors. Code allows you to increase the number of floors, but not the height of the building if you use a concrete or steel podium. Now, mass timber structures can be constructed in any of these categories, type 3, 4, or 5, all of which allow the use of combustible materials. By the way, I showed type 1 in this table as well, just as a reference. Type 1 is your typical concrete or steel building, which is fire rated. It has, they're unlimited in height. If you want to build a high-rise building today, you make it a type 1 building because you have no height limits. But types 3, 4, and 5 structures, especially for the architects and code officials out there, if there are any, those all allow right now in the building code the use of cross-laminated timber, glue laminated timber, structural composite lumber, with various restrictions to build to these same height and area limits in the code. So just as a reference, these values also assume that there's a sprinkler system in the building. There's different, some complexity with what you can actually do. But Right now, type 3, 4, 5, you can go up to 85 feet, depending on the use, up to 6 stories with cross-laminated timber and blue laminated timber structures. Or, as we'll see with RISD, as a little foreshadow, a hybrid of combustible construction like cross-laminated timber and steel. Now, Frank mentioned that coming down the road, a very exciting change in the code is going to happen. It's already been approved by the National Code Council for 2021. Remember, we use the 2015 edition of the code in Rhode Island right now. The 2021 edition, which will be available this year for adoption, creates 3 new categories of heavy timber construction that will allow you to increase that height limit from 85 feet all the way up to 270 feet. So these 3 new types of construction allow you to use fire-protected mass timber columns, beams, and cross-laminated timber or dowel laminated timber panels with these height and area limits for different types of occupancies. So in theory, should Rhode Island, Massachusetts, and other municipalities adopt the code for 2021, we may start to see taller and taller mass timber buildings being constructed throughout the region. Now, I want to be careful here. You should understand that the taller buildings, the taller types 4A and 4B that I've circled here, that allow you to go up to very tall, 18 stories, 270 feet, those require the wood to be covered. So you can't expose the wood like in an old mill building, or like I'll show you we did at the RISD building. You have to cover and fire protect the wood, at least for today with this code. However, portions of it can be left exposed for the 180-foot type building, 180-foot height building, and for the 85-foot high building, you can actually leave all the wood exposed. You just have to show that that charring effect that I described will allow the structure to be fire protected to a minimum value. So very exciting, and we expect to see this in the coming months become more and more popular. Here at O'Day Engineers, we're working on a lot of projects right now that are trying to take advantage of these allowances for taller buildings that are coming in the building code for laboratories, office buildings, residential buildings, largely because of the benefits of sustainability and because of, frankly, the value, some of the cost effectiveness that I'll show you can be achieved with mass timber construction for buildings that are carefully thought out. Okay, so this is just kind of a summary of some of those new types of buildings that are going to be approved. Okay, I'm going to now switch to talking specifically about the example of the RISD project. I want to show you how we built a real building here in Rhode Island out of mass timber. And why we did, and give you some of the characteristics of that building that I think made it very successful as a project. Every project has to be successful on multiple fronts. It can't just be because we think it's more sustainable or just because it costs the minimum amount. It has to meet a client's objectives and challenges. And in the case of RISD, RISD, as I'm sure everybody knows, is one of the nation's great design institutions, one of the world's great design institutions. But its dormitories needed some refreshing. Anyone who lived in RISD Quad, which is shown here on College Hill, knows that this is an older dormitory built in the 1970s and has been renovated a couple of times over the years, but really needed an update for the student housing experience. So RISD has a long-term plan for which they engaged our team. Our team to build this project included NADA Architects, Nadir Tirani, who's a friend and collaborator of O'Day Engineers on many projects. Shamat Design and Construction, who was the builder of this project and the manager of it, and a variety of other consultants that really participated. RISD wanted to build a new dorm that they could use to put some students in while they renovated the old dorm and then make that a permanent new space. And it's right on this site here. They had a very aggressive schedule. That was really important. This building needed to be built in less than 18 months from the commencement of our design process. So that's a very quick schedule. It's about a 50,000 square foot building. We needed to match the environment of the adjacent structures because we're kind of interconnecting with them. And the school really wanted to create a new student life experience, and one that I think underscored and resonated with RISD's goals for sustainability overall in its program, both in its teaching and research, and its student life experience. And mass timber really turned out to be desirable from that standpoint. So this is a model that we, the design team, made, a three-dimensional model before we constructed the building to help design it. You can see here how we chose as a team to construct it. The structure is kind of built into the hill with a steel frame structure at the ground level. That's sort of mostly underground. And then above that level, it consists of steel beams and columns supporting these cross-laminated timber slabs or panels. I'll show you in a minute some of the construction advantages of using that approach. But one of the key advantages that the school recognized right away from using these models like the one you're seeing here is that there could be some great beauty with exposing the structure and really showing off the structural system. Wood, in addition to being a sustainable material, also has been shown psychologically to have very positive effects in residential environments. People want to be in nature. They enjoy seeing wood. It's an effect called the biophilic effect. By the way, these, I'll show you some photos of this, but some of these rooms and amenity spaces have just beautiful views of downtown Providence, which really, in my own humble opinion, is among the most beautiful urban environments in the world. So here's how the frame came together. We used these, as I said, cross-laminated timber panels to build the floors. The structure is a type 1B construction. So if you go back to that table from the building code that I showed you, for the bottom part, and then the upper levels, the 5 stories above that, are built using type 3A construction. And that meant that we could expose the structural steel and the cross-laminated timber on the interior of the building. We had to have a non-combustible exterior wall system, which we created using a metal panel and masonry system and steel studs. And I'll show you how the beautiful design that Nada came up with for that. And finally, the floors themselves, although they're exposed wood from the bottom, on the top they have a thin slab of a cementitious material covered by over an acoustic isolation mat. And that's in order to prevent sound transmission from floor to floor. That's an important issue with design of wood structures. So here I have some photographs of the building coming together during construction. What I want you to notice from this is that the contractor was able to erect the building very quickly because they built the steel frame structure in multiple floors at once. So the steel erector here, using a very light crane because the steel was very lightweight, built several, 2 levels or 3 levels of columns and beams. And then if you see that truck with the white panels on the left side of the screen here, those are the cross-laminated timber panels that were shipped from Nordic Lumber, which is a company in Quebec. They make the product that we use for this project, and they were a key part of our team. Those panels are the entire width of the building. So they're almost 55 feet long and about 6 feet wide. So each panel could be laid in on top of the steel by the contractor by just craning them into place. And I'll show you shortly, screwing them to the steel beams. This is a very rapid form of construction, extremely fast. You can see that that Nordic in their shop, when they fabricated the panels, this is a drone view from the top from one of our drones that we use for construction observations. Pre-cut the holes for the columns. They laid out the joints between the panels such that they could quickly be placed without a lot of fussiness during construction. Here's a quick video that just kind of shows you, this is probably the most complicated, or one of the most complicated panels that we had on the job, just how quickly the contractor is able to put these into position using the crane. And just two iron workers who are laying the panel into place, pre-cut with openings around the columns. You can see the columns are 2 stories high, so they could drop them in and slide them into place in between the columns. So the steel frame, lateral bracing, and columns, along with the CLT, were all constructed by the same erector, which in this case was HB Welding, another Rhode Island, great Rhode Island company, great partner. We worked very closely with them, with HB Welding, the erector for this project, to facilitate practices in construction that would make it as rapid as possible to build this building. You see, using that technique, placing the panels that were very long and prefabricated into place, using steel members that were carefully considered to minimize the number of connections that the contractor needed to make in the field, allowed this structure to be built even faster than we had ever imagined. It's a 50,000 square foot building. The contractor erected it in 2.5 weeks. That's really record time for this type of construction, and it's given this project a lot of attention and interest. CLT, the material itself, may be, per square foot, a little more expensive than using, say, concrete planks for this building, or a cast-in-place concrete slab on a deck, which is the system that probably would have been considered before the existence of mass timber. But if you can build it with such speed that you save literally months sometimes of construction time, just that savings in schedule combined with some of the other benefits can actually make these systems more cost effective than using, say, just a plain steel and concrete structure. So this was a huge win for the client and for the team, and I think allowed us to really make the project a success. Once the panels are erected in place, it's very easy to connect them. In this case, we just use these self-tapping lag screws. You can see that the framers, the wood framers who came in and did all the detailing work afterwards really were able to, this is literally how long it takes to install one of these bolts. The bolts are not in pre-drilled holes, so there's no drilling. The lag screws just go right into the framing. Furthering the sustainability benefits of the project is the fact that there are no ceilings. The ceilings are exposed with this beautiful underside of the cross-laminated timber panels. So therefore, we didn't need to use gypsum, which is a mineral-based material that has a high embodied carbon content, to create ceilings, which would normally be the case in say, a steel deck building of this type, or a light frame structure for that matter. And these are just some more details to show you how the structure comes together. It's beautiful on the underside of these structures. They don't require cross-laminated timber because of the method of cross-lamination using orthogonal layers of wood, means that the panels can actually span in two directions. They're almost like a membrane or a diaphragm. That's an excellent structural property that allows us to create openings in panels and even between panels without a lot of beams underneath them, a lot of supplemental framing. That's very important because it creates a clean and low floor-to-floor height structure. And here's a picture of the finished student bedrooms, which, like I said, create a really great, I think, artist loft type experience. A lot of by the way, the furniture and the lighting in these rooms were custom designed by the architect, Nada, and they're really a sight to see. I'll just show you a few pictures here of the exterior skin. The cross-laminated timber, even in a type 3A building where you have to have a non-combustible exterior wall, is allowed to penetrate through that wall as long as there's a fire-rated assembly that's created at the ends. You have to protect the cross-laminated timber. Using the hybrid of steel and wood allowed us to do some very beautiful masonry work on this building. You'll notice as you drive up College Hill, like Waterman Street, you see these beautiful masonry facades that are very modern, but also evoke, I think, the tradition of historic architecture on Providence's east side. That requires a lot of in and out variation in the brick veneer, and that's easily achieved using steel. So with that, just in summary, I think mass timber is a really exciting building material because of its sustainability benefits, but also the productivity and efficiency of building with mass timber. It's not just about the embodied carbon in the mass timber, it's also about the speed of construction and the design benefits that can be achieved from using it. And I think here at RISD. And I know there are a lot of projects in the planning phase. We're working on some of them ourselves at other nearby schools and for other developer clients where we'll be using a similar system. If you want to see one under construction right now at Brown University, I'm not the engineer for this project, but the new dormitory that Brown is building on Brook Street is being built using almost the exact same system as this. So you can see one of these projects under construction. So with that, I'll hand it back to Scott.
Thank you, David. That was really good. I know I learned quite a bit, and it's exciting, I think, for all of us to learn that what Frank is advocating for is very doable. It's happened right here in Rhode Island, and with innovative engineers like yourself, we hope to see a lot more of this in the future because we need it. With that, we've got about 9 minutes or so left. So CJ, let's open it up to questions for both David and Frank at this time.
Great. Well, I think we can first get to one that we had earlier that we had to wait for until now. And here's the question. How can projects like the North Smithfield Solar Project be avoided? How do we help the private landowners understand and give them options for their private property that does not lead to cutting down the forest?
So maybe I'll speak to that to start. First of all, we have to recognize that for private landowners who own forest land as an investment, unless you have a sustainable forestry revenue stream, then the only revenue streams available to them tend to be development. And that's a failing of our society to value the ecosystem services that private landowners are providing for free to all of us. You know, every piece of forest land is contributing to air quality, contributing to water quality, helping to store carbon, and through the evapotranspiration of the trees, actually directly cooling the regional atmosphere. So those values we all get for free from landowners who are paying taxes and doing maintenance on their land and defending their boundaries. So right now we've got a system-wide failure to provide landowners with financial support for the services that they're providing to all of us. And at the same time, we have a policy failure in the solar sector. You know, there is no doubt in my mind that we ought to be seeing solar canopies like they have at Staples headquarters and REI's Framingham store, and many, many other locations over parking lots where they provide cooling and shade for vehicles and protect from snowfall on part of the parking lot, way before we see new solar system panels going up in forests. Same with rooftops of urban buildings. It's logical that we would put solar panels where we already have development before we put them in forests or farmland. But our incentive systems for solar don't favor that, and they don't, you know, essentially reward developers who put it in those more difficult to work in, more complex situations. It's a lot easier to cut down 150 acres of forest and put a solar farm on it. And it needs to be reflected in the tax incentives and the other incentives available to solar developers that that isn't the preferred outcome.
I just want to jump in. I thought that was an excellent question. GrowSmart has been advocating for several years to provide economic incentives to encourage solar and other renewable energy in developed and disturbed locations, and meaningful disincentives to discourage the continued loss of our farms and forests. Massachusetts just recently took away state economic incentives for solar on their most important forest and habitat. That's going to take approximately 40% of the state of Massachusetts. It's going to make it less economically feasible to build large solar in those areas. Rhode Island really needs to move in the same direction. We need leadership from the General Assembly to make that happen.
Great. So our next question here is, how are the CLT panels joined in the field?
If you let me, I'll just share my screen one more time here, and I can kind of show you a little bit of how it works. But if you notice these lines on the screen in the parallel directions of the panels at their joints, those are spline joints. So there's a reveal left between each panel, and a small piece of plywood is placed and screwed to both sides in the field. That's actually a very simple technique of connecting the panels together. You can kind of see them. You can kind of see the spline joints here before the plywood strips have been placed. Connecting them like that allows the panels to behave as a diaphragm as well. So they do the work that traditionally like a concrete slab might do structurally. It's the kind of preferred and rapid method of building them. They're not set together like traditional heavy timber decking with tongue and groove joints. Their splines are on the top.
Great, thanks, David. So next question here, what news or newsletter resources do you all know of that we can sign up for regarding forest, solar projects, wood option resources in Rhode Island in order to stay up to date with innovation that is going around us as we speak?
So I'll just speak briefly. New England Forestry Foundation has 2 websites, 2 URLs devoted to this topic. Our forest2cities.org site has just been updated and renovated, and I encourage you to go check that out. Our builditwithwood.org is going to have more resources, more in-depth information, and we'll have a blog that links to the latest studies as they come out around the forest and CLT connection. I imagine there are other resources for Rhode Island policy and architectural and engineering aspects.
And I'd add to that, for construction, if you're interested in mass timber construction, probably one of the best resources is an organization called Woodworks. You go to woodworks.org. The RISD project actually is the recipient of a Woodworks award this year, which is great. But you can also see other projects around the country that have been built this way, and a tremendous trove of research on the systems and how they're used in different parts of the world. So it's woodworks.org. I'll type it in on the chat window for those who are interested.
Thinkwood.org is also a useful global resource.
Yeah, that's a great suggestion too.
CJ, other questions?
Yeah, we have one more here. David, I think you addressed this a little bit. We have a kind of follow-up question for you. What about aspects of safety with mass timber products? For example, fires. What is the perception from citizens on this new type of construction?
Like I said, there's been a lot of research and testing that's been done to prove the fire resistance of mass timber construction. It's really important to, the code contains requirements for protecting members in buildings, whether they're steel or concrete or wood. You should know, wood is a combustible material, but its fire resistance, its inherent fire resistance when it's built in the form of mass timber is actually quite impressive. Wood can be shown to continue to, wood floor panels that are of a minimum thickness can be shown to continue to resist structural stresses for multiple hours during an ongoing fire. I would note that unprotected steel, if you walk into a building and you see a steel beam and you see bare steel, has almost no such fire resistant capabilities, because when steel heats up, it rapidly loses its stiffness and strength properties. So that's why in structures that are built with structural steel, they're often covered with that spray applied fire resistant material to improve their fire resistance. So irregardless of the material of construction, it's important and critical for safety to consider the fire rating and resistance of the materials that are used. Mass timber itself represents an excellent step forward in fire safety when it's used properly because of its inherent fire resistance. The general public, perception of fire resistance is a psychological perception. I think what's important is to communicate these values to get the right information out to people so that they understand in plain English how structures behave and how they're designed to protect them for safety purposes.
CJ, I know we're running up on our time limit. I'm certainly willing to stay on if our speakers are. Let's continue to take as many questions as we can.
Just briefly, while we're waiting for the next question, I'm going to share my screen to show one very famous picture of steel beams melted over a wood beam that's still holding things up. Their wood can really be quite fire resistant.
Any additional questions?
That's all right now, Scott.
Okay, hearing none, I'd like to really thank our speakers. I really enjoyed your presentations. I learned so much. I'm sure our audience did as well. It's exciting to know that there are people like you out there, pushing the envelope because this is so critically important. So thank you so much for sharing your time with us today. And thank everyone else for taking the time to join us.
Thanks, everyone. Great questions and really a lot of fun. Thank you.
Tune in next week, everyone.